of like overview of like all open questions about surfaces and four manifolds. I could talk for an hour just about like tori and symplectic structures, except that's light because I don't know anything about symplectic structures, but in principle. Or I don't know, questions about exotic manifolds. But instead I have to start somewhere, so I just picked like a topic. So let's focus on like, what's the best four manifold that isn't just four? Any suggestions? I don't know, what's the best four manifold that's not just four? Do you know?
Best one?
Yeah, there's a right answer.
CP2.
Oh, wrong, no. No?
That's two process.
Really? Come on. No? It's the four ball. Let's start with that. So we'll upgrade eventually, and then it is CP2. That was the next option. Okay, so I'm going to start out by talking about the four ball. There has been a lot of recent progress about surfaces in the four ball in the last few years, which is not necessarily the exact direction that I want to talk about, but I will mention it. So some recent things that I think were particularly notable was the surge of papers about exotic behavior in the four ball. So I told you this open problem yesterday about surfaces in S form. Remember the question was, do there exist a pair of oriented surfaces in S form that are topologically but not smoothly isotopic? We don't know that, but we do know the answer in B4. So theorem, there exist pairs of oriented surfaces in B4 that are topologically isotopic, let's say rel boundary, but not even smoothly equivalent. I'll just say not smoothly isotopic. Okay. And so the first paper about this was actually a paper that I wrote with Juhas and Zemke in 2018 or 19. No, 2019. Our examples were all positive genus. And then Kyle Hayden wrote a paper shortly afterward showing that there were examples of this that were disks, G equal to 0. Then Akbalut sort of realized that he actually had a paper from the 1990s that kind of answered this question for disks. He did produce pairs of disks in the four ball that were not smoothly isotopic. At the time, it wasn't obvious whether or not they were topologically isotopic, but now that we know more about the topological category, we do know that those are exotic examples, and they are a really nice family of examples. I didn't know about that paper when I was thinking about exotic surfaces because it's not phrased like that. This is a cool result. And there's been a lot of increasingly refined results in the last 5 years. So this first paper, we made infinite families, and Kyle Hayden only made pairs of disks. And so it was open for a few years whether or not you could have an infinite family of disks. Now you can have an infinite family of disks. And we distinguished our surfaces using knot floor homology, whereas Kyle Hayden used Kavana homology. So it was open can you distinguish disks using knot floor homology? And yes, you can. And then you can do equivariant things, and you can use any kind of flavored knot floor homology that you want. And I don't even really know what a good open question to ask about this now. It's you take your favorite kind of 3 adjectives floor homology, and then ask if that can detect exotic disks in the four ball. That's probably a paper. So think about that. But another thing you could do is think about what if I put increasing restrictions on the surfaces? So they're not just oriented surfaces. I'm going to make them be embedded in a really trivial way. Okay. So there was a paper that I read a few years ago with, there's a lot of them. Let me think about this. With Kyle Hayden and Salon Kim and Tung Park and Isaac Sundberg, where we answered the following question. I guess I won't say it's a question. We showed that there exist Seifert surfaces in S3 that aren't isotopic in B4 once you push their interiors into B4, so that question makes sense. So with interiors pushed into B4. even topologically isotopic. And we also find examples that are topologically isotopic but not smooth. And when I say we make lots of examples, we give lots of pairs of Seifert surfaces. We also give infinite families of Seifert surfaces, two, I guess. But the difference between those, and I'm going to tell you an example of one of these pairs of surfaces that will illustrate maybe like what the problem is that we make pairs with boundary not, or with boundary not, and okay, we make pairs with boundary a link with more than one component, and infinite families with boundary a not. And so there's still some room in here to try to construct an infinite family of Seifert surfaces with boundaries a not. Okay, so I'm skipping ahead a little bit. This is like sort of the general thing that I'm going to talk about for like the next like 20 minutes or so. But I do want to convince you that this was like interesting because you've never seen this statement before, and I'm just like, okay, there's Seifert surfaces that aren't isotopic in the floor ball. That's like, why would, you know, like, why would you expect them to be isotopic? That's kind of weird. The point here, and we talk about this in the paper, and this was observed by Livingston in the 70s. He wrote this really cool paper where he proved that any connected, or I'll say any two connected genus G surfaces, Seifert surfaces for the unlink, specifically, are isotopic rel boundary in B4. And the in B4 is really important. I don't think it to be true for knots. I think for the unlink, I don't think, can I give you an example? Yes, I can. I can give you an example of why it's important. So here's the unknot. That's the best unlink, by the way. Okay, and I'm going to draw two different Seifert surfaces for it that are not isotopic in S3. But they're going to be obviously isotopic in B4. Okay? So here's the surface 1. This is just a genus 1 surface. Think about like a closed genus 1 surface embedded in the standard way in 3 space, and I just deleted a little disk. So I get something with boundary, the other not. Right? Here's another genus 1 surface with the same boundary. How about, I'm going to take a torus that's tied in the shape of a non-trivial knot. And just like before, cut a little hole in my torus to get something with a boundary component, which is an unknot. So these are each genus 1 surfaces, and they have the same boundary. And they are definitely not isotopic in S3. I know they're not isotopic because the traditional thing to do would be to compute the fundamental group of their complements. They are not isomorphic to each other. Something else that I might say in this case is that, well, any knot, any curve that fits on this blue surface is a torus knot. So anything that I could draw here is just some torus knot. Okay? But on the other hand, on this red surface, I've specifically tied it in the shape with the figure 8 knot, which is not a torus knot. So I have a curve here that's a figure 8 knot. So if these two surfaces were isotopic, then that would give me an isotopy from the figure 8 knot to some torus knot, and that doesn't exist. Okay. So then we don't even have to do the fundamental group computation. On the other hand, it's actually really easy to explain why these two surfaces are isotopic, rel boundary, once we push their interiors both into B4. Because once I have a 4th dimension of freedom, I'm allowed to do crossing changes. Like the issue in S3, sometimes psychologically, like why are these isotopic? Well, clearly they would be isotopic if I were allowed to take one of these crossings, these like 2 red tubes, and change the order of which one were in front. Right? If I were able to unknot the figure 8, then this would all come undone. Well, now that I have a 4th dimension of freedom, I'm going to take this like back strand, this tube that's behind the other inside of this red torus. I'm going to push it really deep in the 4th dimension. And now that it's in the 4th, it's somewhere deep in the 4th dimension, in 3 space, it's okay to pull it forward. Because it won't actually cross through this, because they're in different cross sections of like the fourth axis. Does that make sense? Okay. So that means once I have a fourth dimension of freedom, I can change this crossing, and now they're isotopic. Okay. So in this paper, Livingston observed that there were much more interesting examples in the literature at this time of Seifert surfaces, and I said 1970s, but I just realized it's like 1980 exactly, so almost. There are lots of examples in the literature of Seifert surfaces that weren't isotopic to each other. So who's read Robson, the textbook? Ish, just a little bit of it. Okay. I thought that would be more popular, actually. That's okay though. I mean, it's fine. It's a pretty good book. But it has this like really nice example due to, I think this is by Trotter. This is probably like the most famous example of like two Seifert surfaces for the same knot that aren't isotopic in S3. And they're a much more interesting family of examples because the ones I'm going to give you are minimum genus. As opposed to, well, these are genus 1 surfaces for the unknot, so it's fine, they're not isotopic, but I also don't care about them because the unknot has a disk, right? Why would I care about these? So let me give you the minimum genus examples from Trotter. So I'm again going to give you a knot, but it's going to be a more complicated knot because I need it to not bound a disk anymore. I need its minimum genus surface to be more complicated. So here's a pretty good knot. I could have something that has like a clasp, and then tie this band in the shape of a trefoil. Okay, I did not practice that beforehand. That went pretty well. Okay, so here's a knot. I'm going to make a minimum genus surface. And I'm going to build my minimum genus surface so that at some point I have a choice, and I can make two different choices to get two different surfaces. Okay? But I'm going to start off the same way no matter what. I'm going to start off by adding to this picture temporarily two more components. A red knot that links my knot like this, and I hope green's okay, but a green knot that links my knot like this. Okay. And I'm going to start building a Seifert surface. And at first, the boundary is going to be all three of these circles, because that I think just makes it easier to see what's happening. So near this red circle, what I'm going to do is take a surface, like a planar surface, whose boundary is on the red curve and part of the black curve. And see how the black curve goes behind as I go from left to right here? This red is just going to go behind until it goes through the green circle. So far I've built a surface whose boundary is on red and black. And at this point I have this long strip that I can flip over. And it's tied in the shape of a trefoil. And then eventually my long strip goes through the red circle and ends at the green one. Okay, so what do you guys think about that? Are we okay? It's like maybe a slightly intimidating picture. But so far it's not that bad. So here's where I'm going to make a choice. Right now I have three boundary components, but I only want to have one. I need to attach some more surface so that I don't actually have these red and green boundary components. And the way that I'm going to do that is by attaching a cylinder whose boundary is the red and green circle. So I'm going to have two choices of cylinder. One of the cylinders is going to be a long tube that just follows the shape of this trefoil knot. I feel like the orange marker kind of let me down here. Can you all see the tube? Is it bad? Okay. Once I attach the tube, I will get a Seifert surface for my knot. It's genus 1, so it's definitely minimum genus once we believe that this isn't the unknot. I think we could believe that, maybe. But you can compute the Alexander polynomial. Here's another tube with the same boundary, but the tube's going to be different. In fact, the tube is better. I'm going to make my tube be like really wide in the middle, so that instead of following this trefoil path, I'm going to have my tube have a huge bubble. And it just ignores the trefoil completely. That looks exactly the same as orange. ignores the trefoil completely. Okay. So I build my two Seifert surfaces by taking my first surface, like I didn't name it, but add one of these two tubes, and we'll get a genus 1 Seifert surface. So these are both minimum genus. And in Trotter's paper, which was the 70s, I think, it could have been the late 60s, but I think it's the 70s, he constructed this example and proved that these two Seifert surfaces are not isotopic in S3. And the way that he did that was compute the fundamental group of their complements. That's why it's a traditional thing to do. And even though the surfaces look really intimidating, it's not a very difficult computation. I mean, the surfaces that I built basically look like thick trefoils. The group you get kind of looks like a trefoil group. It just like looks bad, but it's not hard to do. Which is nice. It's like the opposite of what usually happens, right? Okay, so they're not isotopic in S3. And this is, I think, one of the examples in Rolf's, and this is why it's interesting. These surfaces, even though they're very different, they do become isotopic rel boundary once you push the interiors into B4. And it's the exact same logic as before. The only difference between these two surfaces are these tubes. One of the tubes was knotted, tied in a trefoil, and the other one wasn't. And in S3, I don't have enough dimensions of freedom to get rid of that knotting. Like this knotted tube is linked with itself, and it's linked with the knot. There's just like a bunch of stuff that's in the way. But once I have a fourth dimension of freedom, I can take my knotted tube and push it really far into the fourth dimension, and now there's nothing in the way anymore. I can change those crossings, and they're isotopic. So Livingston observed that this was the case for like essentially all examples in the literature at this point that he was aware of. Surfaces tended to become isotopic in B4. And he had this paper where he showed, well, that's a general fact for unlinks. Surfaces become isotopic in B4, connected surfaces. And so he phrased it as more like, well, surely it can't be the case that this is true for every knot or link in S3, but he didn't know how to make the example at the time. Okay. So I'll write like question of Livingston. Is this always the case? And so I've already spoiled the answer by writing this theorem that says, no, there do exist Seifert surfaces with the same boundary that aren't isotopic even when you push them into B4. And in fact, it's very refined behavior. There's some that aren't topologically isotopic, some that aren't smoothly isotopic. There's even infinite families. Let me at least give you like the simplest example of this happening, and then I'll like directly write the open question that I don't know how to answer. So the simplest example, which I do feel bad that I'm saying simple. Okay, so I'm going to draw two Seifert surfaces whose boundary is the same knot. Can I draw a knot? Yes, maybe. So I'm going to start off by drawing a knot. Okay. Just ignore me for a second. It's going well. Yes. Okay. We're good. Okay. Don't think about it too hard. And then, if you think it's a trick, don't worry. And then I'm gonna draw another copy because I want to see two Seifert surfaces at the same time. And now that it's really complicated, it's not going to work as well as in one of these two pictures. So I really think I just need two copies of the knot. And you'd think that like the second time would be easier, but typically like somehow I get really confident for the first one. After the first one, oh no. Okay. There we go. Okay. Does anybody see a problem with this knot? I see it. I see it. You're doing it. Yeah? What's the problem?
Two components?
Yeah, it's a link. Okay. So that is going to be a problem. We'll fix that. But let's start off, and this is modeled on a paper of Leon from the 70s. I want to put that out there. He constructed more examples just like Trotter, but his were hyperbolic boundary. So again, just like put your favorite adjective. There's probably room. So here's two Seifert surfaces for this link. And these are going to be isotopic. Maybe not if I say rel boundary, but these are isotopic even in S3. So really what I've drawn here is a torus link. This is the, what is that, 6'4" torus link or something? This is a link trefoil. Okay. So because this is a torus link, it sits on a torus, and it cuts the torus into two pieces, which are both annuli. So I'm going to start off with just those two annuli. Okay. So my annulus looks something like this. Yeah. Okay, so all I did was take straight lines connecting adjacent pieces, and I got this annulus that's tied in the shape of a trefoil. Okay? Well, on the other hand, in my annulus, I chose, like somehow this strand and this strand are going to be connected by a cocore. But what if I made the choice that it's going to be this strand and this strand that are connected by a cocore? So when I take the whole picture and I rotate pi over 3. Okay, so that's totally fine. There's a symmetry. And if I do that, I'll get exactly the same surface rotated. It's just another annulus shaped like a trefoil. Like somehow the core of this one is a trefoil shaped like this, and the core of this guy is a trefoil shaped like this. That is invisible. Trefoil shaped like this. Still a trefoil, just, moved. Okay? And the boundary is a link. So let's fix that by connecting the boundary, but making sure that they still have the same boundary. So in both pictures, I'm going to attach exactly the same, just like a band, like a strip of paper. Just to make sure the boundary is connected. Okay, but I broke the symmetry when I did that. Because if I look at how the ends of this band sit relative to this surface, this blue band, both of its ends were attached to the same, petal of the trefoil. They're both on this top piece. But this red band, it's actually really far apart in this annulus. They're on different petals of the trefoil. So it's a pretty simple exercise, actually easier than in this case, and this was Leon's point, that the complement of these two surfaces in S3 definitely not homeomorphic. The fundamental group is the complement of these two graphs. And you might know that, like, oh, this graph is unknotted in space and this one isn't, or something. Like, the groups are not the same. What's not so obvious what happens when you push into B4. So what we prove in the paper, these are like our first examples, are that these two surfaces are not even topologically isotopic in the 4-ball, because when you take their double branched covers, the two 4 manifolds you get aren't homeomorphic. We just computed the intersection form. It's like a really basic invariant. They're not homeomorphic. And using the same sort of symmetry idea, we give lots of other examples that are higher genus. It's not so obvious from what I've said here how to get infinite families, but we did that. In fact, I will tell you one infinite family, which is a cheating one, because I'm going to give you a family that's disconnected, but they don't have to be. Here's a family of Seifert surfaces that are not isotopic real boundary in the 4-ball. So these surfaces, not isotopic real boundary in B4. So their boundary is going to be a 3-component link. What's the best 3-component link? Down link? Yep. Okay. I'm sorry. Okay. And I'm going to take a surface with this boundary, and I think specifically I'm going to take a disk and an annulus. So this is going to be like surface 0. I'm making an infinite family. It's disconnected. Sorry. We do have connected examples, but it's just a little harder to draw because it's just a bigger torus thing. And what I'm going to do to get the other elements of this family is take a torus that sits in the complement of this unlink, but not in the complement of the surface. I'm going to take a torus like this, where 2 of the unlink components are on one side and 1 is on the other side. Okay, and what I'm going to do is consider, well, it's my base surface, sigma 0, and I'm going to get sigma n by twisting it n times about this torus. So when I say twisting it, I mean that I'm going to rotate all of space about this meridian direction. so that whenever I have, just like yesterday, an arc that passes transversely once through the torus, after I apply one twist, it transforms into an arc with chalk. There's like more colors. It transforms into an arc that twists one time about the torus. Okay. I think it's like maybe a little bit hard to visualize the whole surface at once if you haven't seen it before. So just like convince yourself that that is a homeomorphism I could apply to space and it doesn't move the boundary, so it's fine. Okay. So we show that these surfaces, like as long as you twist more and more times, are also not even topologically isotopic in the four-ball real boundary. So these are not. So sigma n obtained by n twists. And sigma m and n, I always wrote a and b, and for some reason that felt wrong, like they're not integers. Sigma m and n for m is not n are not isotopic. And again, the abstraction comes from a homology, the homology of the double branch cover. And so we do give exotic examples too. I won't tell you what they are. It's a little harder to define. Pretty easy to draw still. And the abstraction in this blue category is Kavanagh homology. But the reason I drew this is I want to point out that somehow, like intuitively, the reason that I can't undo the twisting in the fourth dimension is that this link has boundary components on both sides of the torus. Like, I'm just twisting about this like trivial torus. If I were allowed to move my link, these surfaces actually are isotopic, so I can just sort of undo the twist. The issue with that is, well, these two curves here, if I undo the twist, I'll have to like twist them, move them in space, and that's not allowed. So we fundamentally do not know, question, do there exist, or does there exist, an infinite family of Seifert surfaces for a knot in S3 that are not isotopic real boundary in the four-ball. And it's not an exotic question. I don't even know how to do this topologically. And after we wrote this paper, there's an excellent paper follow-up by Aka, Feller, a different Miller, and Park maybe, where they, not him, Weiser, and they showed that there's many more examples of this behavior, just sort of like really going hard on the algebra part of distinguishing the homology of the branch covers. But again, like for a very fundamental reason, even in the follow-up paper, they cannot answer this question, and I have no suggestion for how to answer this question. And every once in a while, someone emails me an idea about it, and then I just like have to send back a response like, well, here's why that doesn't work, and that's a bad feeling. But like, so if you send me an email, I'll tell you why it doesn't work, you know? But I'll be really happy if it does. Like, if somebody answers that, I think that'd be awesome. Okay, so that was the open question. I wanted to tell you about the best four manifold that isn't this form. And now we're going to go to the lesser example. Okay, so let's talk about CP2. And in fact, this is also going to apply to other four manifolds, just somehow CP2 is a focus. Erase this. Okay. So, I think now I want to talk about the genus problem. So, let me remind you, in fact, we heard this in a talk yesterday. This is true, that every second homology class in the four manifold is represented by an embedded surface. I think this is an exercise in chapter 2 of Knowledge Dipshits. And Dylan Thurston has a really nice explanation of why this is true on Mass Stack Exchange. I won't explain why it's true because I think you all know that it's true. And in particular, a very classic thing to do is to study what's called the genus function. The genus function takes an integral homology class And I'm just going to output, and I'll call this like gx. And I guess it's okay if it's a torsion class, but we just don't usually think about those. But I'm going to output what is the minimum genus of a surface embedded in X with, min G, sigma, sigma is equal to G, and sigma represents this homology class. Yeah. Okay. So for every immigrant homology class, I get a non-negative integer, which is just the smallest possible genus that I can use to represent that class. And this makes sense in both the topological and the smooth category. And most of the interesting questions that I could ask you about are in the smooth category, so I want to focus on that setting. So this is a hard problem in the smooth category. In particular, we know the answer for a relatively small family of four manifolds. The best known examples are the fact that we know the genus function on CP2. So this is going to be a theorem of Kronheimer. Usually I just sort of scribble so you can't tell if I'm spelling it right. Kronheimer and Rufka, 1990s, where they found that this, CP2 second homology is just Z, so usually I just write the second homology class as an integer, D for degree. This is D minus 1 times D minus 2 over 2. Okay, and then the zero class always says genus 0, so that's not interesting. This is like the landmark paper. And then a nice observation, but a much simpler observation of Danny Ruberman is that, and I won't write the function because I kind of don't remember what it is, but we do know the genus function on S2 cross S2 and CP2 connects some CP2 bar, which is basically the same thing. And these aren't literally the only non-trivial examples where we know the solution to the genus function. There's a cool paper from like last year by Stipschitz and Szabo where they give many examples of four manifolds of the same genus function, but those four manifolds are homeomorphic but not diffeomorphic. But I don't have like good names for those four manifolds. On average, if you give me a smooth four manifold, it would be very difficult for me to answer this question. I give you bounds if it's like a symplectic manifold or a complex manifold, but if it's neither of those, then I really don't know how to do anything. So the usual case that people focus on when you're talking about sort of open questions related to genus and closed four manifolds is the third best closed four manifold, which is CP2 sum CP2. Okay, so we don't know this. And I'm going to convince you that this is an interesting problem. So first of all, the second homology here is just Z squared, right? So I could very naturally write a second homology class as just a pair of integers. And maybe I should say the manifold still to CP2. Well, it would be very natural to guess that this should just be the sum of the minimum genus coming from the first summand and the minimum genus coming from the second summand. This is clearly an upper bound because if I wanted to find a surface, so this is question mark, if I wanted to find a surface into CP2 that represents the class AB, then I could just take even a disconnected surface of class A in the first summand, class B in the second summand, and then I'll join them together if I want to make it connected, just to make me happy. It doesn't really matter, but clearly the genus will be additive. Okay, who already knows the answer? Anybody? No? Okay, so any guess? Guess? No? This is not true. It's a very good guess, and it fails immediately. So the problem is, no, the genus, and when I say fails but I don't immediately know the genus is 0. If the genus of A and B are both 0 in CP2, well then of course that's going to give me an upper bound of 0, but then it just is 0, so that can't be the counterexample. So I need to take the first homology class where at least this number isn't 0, and that would be the homology class 3, 0. So in CP2, the 0 class is represented by a sphere, but the 3 class, when I come to look at the Thom conjecture formula, it's represented by a surface of genus 2 times 1 over 2, which is 1. So this guess would tell me that the genus, minimum genus of a surface representing this class should be 1. And that's false. There's a 2 sphere smoothly embedded in 2 CP2 that represents this homology class. And there are lots of different ways that we could think about it. Depending on how comfortable you are with like complex surfaces in CP2, maybe you know that there is an immersed 2 sphere in CP2 representing the class 3 with 1 intersection, and I'm blowing up that intersection. I'll say that for some people. If you don't, what am I really doing? Well, maybe I'll draw it like this. Here's a construction of 2 CP2. Okay. I have a 4-ball. Up here I'm going to have another 4-ball, and I'm going to glue them together along 2 CP2 minus 2 4-balls. Okay, that's fine. But now here's a surface. I'm going to make a 2 sphere, and at the bottom I'm going to have an unknot bounding a disk. Okay, but I'm going to draw my unknot in like a funny way. I need more room for my unknot. B4. Okay, I'm going to draw my unknot like okay. I got too close to the edge there. This is a 4-crossing diagram for the unknot. I think that you can probably check that this is the unknot easily. Like, see, there's this Reidemeister 2 move that I can do to get rid of these 2 crossings. And then I can do a Reidemeister 1 to get rid of 1 more, and another one. It's the unknot. And at the top, I'm going to have another unknot bounding a disk. So this is the schematic. This is the schematic. And in the middle, I need to fill in here an annulus that's contained inside of this 2 CP2 minus 2 4-balls. And the boundary needs to be 2 unknots. Okay, so what am I going to do? Well, to build 2 CP2, what I do is attach to this bottom B4, the 0 handle, 2 handles, which are each attached to 1 unknots that are split from each other. They're each attached with framing 1. We saw some Curry diagrams the last few days, so I feel a little bit more confident. So I'm going to attach a 2 handle around a curve that looks like this. The effect of doing that, like if I want to think about what does this do to the surface that I'm building, is nothing. Except, once I go above the 2 handle, so let's put another cross section here. That's going to leave not enough room. Once I go above the 2 handle, so this is just 1 CP2 minus B4. And on the top we'll have the other one. Is that, well, this disk, I can just extend upward like a collar to make a bigger disk. But the boundary won't look exactly the same. It'll be this knot, except wherever it linked this attaching circle, I'm going to add a whole twist. Okay? And I'm specifically arranged so that that twist goes the opposite direction of these 3 strands. So I'm going to get something like my original knot, looks exactly the same. Okay? But now where I link these three strands link this circle, I'm going to add a full twist. Okay? I know that looks complicated, but see how this strand goes over and then back over? A lot of this cancels out. Okay? Really what I've done here is I pretended that this crossing was the other way around, so that this was a trefoil. And I've just given you a twisting that if I applied it would sort of undo all this positive twist with all these negative twists. And then simultaneously, here at the top, I guess, I'm going to twist one more time. But I'm going to twist specifically so that I change this like weird crossing that doesn't match the other ones. So I'm going to grab those two strands, and I'm going to twist to change which one's up. Okay, and when I do that, I just claim that I'll get another unknot. That's something that you can check if you wanted. And so altogether, I've built for you a very explicit diagram of a surface sitting inside of 2CP2. And it's definitely a two-sphere. And it's really easy for me to check what homology class it represents. Because CP2 is so nice, its second homology is generated by CP1, right? So all I have to do to check what homology class a surface represents in CP2 is measure how many times it intersects CP1. Like CP1 intersects itself once, it's the generator. The zero sphere doesn't intersect it at all, it's zero. If I take twice CP1, the quadratic intersects it twice. Perfect. So how many times does this two-sphere intersect the two CP1s is just measured by how many times it links these two curves that I drew. And, well, if I orient this knot, it links this curve 3 times, and it links the other curve 0 times, because these two strands are going the opposite direction. So this represents the class 3, 0. Which for me somehow felt easier than the blowing up thing, but I guess it's not. So maybe just take the immersed sphere and blow it up. It's fine. But I really like this example. And so now you might guess that it's always less than the standard guess or something, or at least like outside of the trivial cases, but that's not right either. Because the genus of 2CP2, 3, 1, so but, is equal to 1. Which is, again, what we should get if we believed the naive guess and used this formula, because the genus of class 3 in CP2 is 1, and the genus of class 1 is 0. So sometimes it's additive, sometimes it's not. And there is like a way of saying that, in fact, sometimes it's really not additive. So this is something that we don't understand very well yet. But I think the best result about this not being additive is a paper from 2 or 3 years ago by, again, it's a lot of people, Theorem, Morathon, it's a different Miller, and it's a different Miller than the other one that I mentioned before, but they're both Allison, so that's like a bigger problem for them. Shipshits. And you know what? It's some combination of these people. Right. Teichner, Krosky, I don't remember. Okay. They proved that if A is bigger than 3B, then the genus of class AB in 2CP2 is strictly, that would be weird, strictly less than the genus of class A plus the genus of class B. Okay, so CP2. Okay, see, so that didn't work in the class 3-1. It was additive, but it's like right on the line of this equation, so that's okay. And in fact, as this difference becomes large, they show that this difference can be arbitrarily large. So it's really not a very good guess. But what's not clear is what happens on this line, or under the line, but I think the line is particularly interesting, when A is equal to 3 times B. We do happen to know, from a paper in the 1990s by Brian, that the genus of class 6-2, the next element on this A equals 3B line, is 10, which is indeed the expected genus of A plus B. If we go back to our formula, minimum genus for class 6 in CP2, I mean it's 6 choose 2, which is 10. And the minimum genus for class 2 is 2 choose, it's sorry, 6 minus 1 choose 2 is 10. You gotta comment on that. It's 5 times 4 over 2. That's definitely 10. And the genus of class 2 is 1 times 0 over 2, which is 0. Okay. But it's not known what happens higher than this. This is the last one on the line that we know. And the reason that I think that this question, and I'll write it explicitly question, is the genus 3B, B, always equal to the genus 3B plus genus B. Interesting is that, I mean, of course this is a topological problem, but like, kind of not. It has like an application that would actually be like, feel, I think, much more topological. So this is not going to seem related at all. You guys know how the figure 8 knot isn't slice? Here's like the most roundabout proof of why the figure 8 knot isn't sliced. This is totally unnecessary. You can compute its Alexander polynomial, get its determinant. It's really easy to prove that the figure 8 knot isn't sliced. But pretend that you don't know, okay? The figure 8 knot would prove that it's not sliced. So here's why it's not sliced. Or at least I'll tell you how you could prove it. I'm not going to do a bunch of not isotopies because I don't think people like that. But this is a way that you could prove the figure 8 knot is not sliced. What you could do is, well, remember that we did this whole painful thing where we explicitly got a surface in 2CP2. And let's do that again. But not the whole thing. But I saw that what I had to do in order to get a surface was start off with like a knot, like the unknot, and show how to apply 2 whole twists to that unknot and get another knot, which happened to also be an unknot. And then these 2 knots, the one that I started with, the one that I ended with, I could cap off in the 4-ball and get a closed surface. Okay. So I'm going to do the same thing. Let's suppose it is. Then in my setup, which I'm not going to draw the middle like before, I could build a surface where I start off with the figure 8, okay? And I could cap it off in B4 with a slice twist. And this could be my starting point for building a surface in CP2. Like now my goal is to apply twists to the figure 8 knot to turn it into something else that I can cap off. And I'm going to show you specifically how to turn it into the unknot, which I can definitely cap off with a disk. 2 twists. And if I do this, I'll get a 2-sphere inside of CP2 or 2CP2. And then I can check if that's okay or not based on the homology class. Okay. So here are the 2 twists. This is the only information that I have to tell you. So what does the figure 8 knot look like? Well, okay, that was a bad start, right? I know how to do the figure 8 knot, it's right there. So this is unobjectionably the figure 8 knot. Like we're all cool with that, right? So that means that if I did this, it's still the figure 8 knot, right? And if I did another Reitermeister 1 move, it would still be the figure 8 knot. Okay, we're all good. I claim that if you twist about these 2 unknots, you turn the figure 8 knot into an unknot, which I think is like a really cool trick. That's a little exercise you can do. It's not out of nowhere. It's actually out of a paper by William Bollinger. It was awesome. But really what you should think is the first twist here is to change this clasp, turn this into a trefoil. And the second twist is based on the fact that the trefoil can be unknotted with 1 twist. So it's not a random guess. But I just claim that this is true. I won't draw the isotopy. But I will check what homology class does the sphere that I get represent. It's based on the linking numbers of this figure 8 with those 2 circles that I just drew. So I oriented so that I could compute the linking number. And I see that, well, this lower circle, I see that it links 3 strands of my figure 8. And when I orient, all of those strands are pointing in the same direction. So the linking number here is 3. So I get a sphere in 2CP2 that represents the class. Okay, so the first one is 3. And now I need to check how does this link the other circle that corresponds to the other CP2. So it still seems to link 3 strands of my knot. But when I oriented my knot, they did not all point the same direction. This one goes up, the other two go down. So that means the liquid over there is 1. But there is not a 2-sphere that represents the homology class 1. So that's a contradiction, so the figure 8 knot isn't sliced. And you only have to know Roupling's theorem. So it's not a very good proof, but I think it's very funny. And the reason that this is interesting is even though this isn't a very good proof, we used the exact same strategy in a paper to prove so theorem 2023. I'm going to cite someone else too, don't worry. Cheto, Castro, this is my aim square. Things are going poorly at the moment. We're very stuck with orientations. This first one was okay. We showed that if the genus of the class 3, I'll write it as an even number, 6A, 2A, or 6B, 2B, is equal to the sum, then instead of the figure 8 knot, I'm going to take a cable of the figure 8 knot. The 2B1 cable of the figure 8 knot is also not sliced. And it's the exact same argument. I just take like literally this construction and I sort of cable the whole thing. And so this was exciting for us because, well, you see, we know this Bryan bound 6-2. So when I come and apply the Bryan theorem that says, okay, well, this is true in the case that B is equal to 1, that tells me that the 2-1 cable of the figure 8 knot isn't sliced. And it's like a very easy proof of it. Unfortunately, somebody else got there first. I'm just kidding. It's this guy. But earlier than that, Dye, Malik, Park, and Stoffergen had proved in at least a totally different looking way that the 2-1 cable of the figure 8 is not sliced. And this really was a big deal. I mean, this paper was written up in Quanta. The reason it's a big deal is that it was already known that the 2-1 cable of the figure 8 knot is not ribbon. There's like a really cool proof. It's a consequence of Casson and Gordon, explicitly shown for this knot and many others by a previous Casson-Gordon grad student, Miyazaki, that this cable cannot be ribbon. But because of the symmetry of the figure 8 knot and the fact that we're taking an even cable, it happens to be that this cable is rationally sliced. It does round a disk into a rational homology ball, and so all of the usual slice invariants vanish. It's very hard to prove that it isn't sliced, but it isn't ribbon, so if it were sliced, that would have been like better than Quanta, right? That would have been the slice ribbon conjecture. But it's not, which is too bad. And their argument was very specific to the 2-1 cable. That symmetry applies to the any even number 1 cable. All of them are not ribbon, but they look sliced. Like their slice invariants all vanish. And we still don't completely know. It's been extended a little bit. Or recently, this guy again. Kong, Park, and Taniguchi. Showed that the 2B1 cable is not sliced if B is 2 mod 4. So we still don't totally know. These are like some really interesting potential counterexamples to the slice ribbon conjecture, these particular cable knots. There's like a very good reason that this proof only works in the 2 mod 4 case. So we know that the 2-1 cable isn't sliced. We know that the 6-1 cable isn't sliced, but the 4-1 cable still kind of looks sliced. Yeah. So I think it'd be really interesting. Well, if you prove that this bound is additive just for the specific homology class, it would be cool from the point of view of people who study surfaces, just like the genus function, because This is like sort of the mysterious case in 2CP2, or like the borderline of what we do know about. It would also tell you that some knot is not a counterexample to the slice-Rubin conjecture, which is like that's good, or bad because that conjecture is not true. On the other hand, if you showed that this bound isn't additive, it wouldn't disprove a slice-Rubin conjecture. Yeah.
I think B should be off here. Q times the not.
Oh yeah, sorry, I put the 2 here. Yeah, thanks. Slice if B odd. Thank you. But so question, very specific question, is the 4-1 cable of the figure 8 slice, which I do realize is a question about B4, and I said I wouldn't do that again, but like really what I care about is the genus of the like 12-4 homology class in 2CP2 additive. Is it genus of 12 plus genus of 4? Okay. All right, so I think I'm out of time. It's like 10:45. I should stop. Thank you for having me. Two open questions.
Any questions about the questions?
Or do we not even know that the genus is literally
It's unbounded in the smooth case. Oh wait, sorry, you're in the closed. I'm so used to thinking about slice surfaces. Yes, yeah. Do we know that it's unbounded? I'm pretty sure in the smooth case, yes, and in the topological case, no. I mean, the topological case, we know that it's not. But I kind of don't remember for the. I don't remember for sure for closed manifolds. Definitely the bounds are different. I do think we know that it gets large. I'm mixing up the question with a lot of recent results about the minimum genus of knots into CP2 or 2CP2. So it's been like 10 minutes after the talk. Yeah?
Maybe sort of related to that, and I know nothing about knot theory and all of this, so this may be a really naive question, but is there any way to think about like the growth rate of the genus function and to say, okay, maybe if there are bounds on the growth, somehow we can determine what surfaces could show up with that?
I mean, I think that's a really interesting question. It's a little bit weird because it's like, I don't think it's even necessarily monotonic, I mean, I do think it would be very interesting to like quantify, like, does it grow, or like, I don't know, fix like a particular line in this plane. I mean, yeah, it's very interesting. Yeah?
Okay, so T1 cable was a candidate to disprove the slice indicator. What are the significance for one cable?
Well, it's just also a candidate.
Oh, also.
Oh yeah, the Miyazaki, the argument for why it's not ribbon works for any cable of the figure 8 knot, no matter what parameters, is not ribbon. It's just only really interesting in the case of even number comma 1 cable, because then those knots are rationally sliced. So the 4-1 cable is definitely not ribbon. It's definitely rationally sliced. These arguments don't work to prove that it isn't sliced. Yeah. Good question.
Okay, let's thank our speaker again.
You should thank the organizers one more time.